So the classification of acids and bases as weak or strong is going to depend on how much the actual acid or the base dissociates in solution. When we refer to strong acids or strong bases, those are strong electrolytes, which means that they dissociate entirely in solution. So instead of having the molecule of the acid or the molecule of the base, what you have in solution is only the ions. Looking at weak acids and weak bases, the dissociation is a partial dissociation, which means that we have weak electrolytes for these ones. And when you have a partial dissociation, it means that in solution what you have is mostly molecules without dissociation. So if I'm using here HA to represent a weak acid, when you put your weak acid in water, for example, that's an acid, and the acid will donate the proton and the water molecule will be accepting the proton. So the acid donating the proton to the water molecule is going to give you the hydronium ion and the negative part of your acid, which is going to give you the conjugate base of the acid. So a representation of a weak acid in water, it's going to look something like this here, where you have a lot of your molecules for the acid, and I have here just a few ions, the hydronium and the conjugate base, that is coming from the dissociation of the acid. So this is like a representation of what's happening at the molecular level. So most of your acid will remain as a molecule, and you will get just a few ions in solution. And something similar will happen if you have a weak base. When you have a weak base, your base is going to dissociate partially. So base here will be accepting the proton from the water, because remember, water, it's amphoteric, which means that it can act as an acid or a base depending on the substance that you have combined with the water. Since you have combined with the water a base, the base will be accepting the proton from your water molecule. And then you're getting here your protonated base, because the base is gaining the proton. And then you have here your hydroxide ion, which is coming from the negative part of your water molecule. We can represent the water molecule as your proton, the positive part, and the negative part, which is your hydroxide. So if the proton is going to the base to give you that one there, what you have left is the negative part of your water molecule, which is the hydroxide ion. So I have here a similar representation to what I have for the weak acid. In solution, you have mostly your base, the molecule of the base, and then just a few ions, which is the products of your reaction. So when you have weak acids or weak bases, you're going to have them in equilibrium. When you have strong acids or strong bases, your strong acids are completely dissociating in water, so you only have ions and you don't have an equilibrium. You have a single arrow pointing towards the product side, and the same thing happens with your strong bases. Since we have an equilibrium here for weak acids and weak bases, whenever you have an equilibrium, you're going to have an equilibrium constant. So for weak acids, we have a Ka, and that Ka means that that's your equilibrium constant for the dissociation of a weak acid. We have something similar for weak bases here. You have Kb, and Kb means that that's your equilibrium constant for the dissociation of a weak base. You don't have an equilibrium constant for a strong or acid or a strong base because you don't have an actual equilibrium. So using my generic equation here, you can write down your equilibrium constant expression for the dissociation of your weak acid, your products, your hydronium ion, the conjugate base, and then on your reactant side, what you have is the molecule of the acid. Water is a pure liquid, so we don't include that one in your equilibrium constant expression. For my weak base here, I have a generic equation here representing the dissociation of your weak base in water. So you have the base accepting the proton to give you here your protonated base, which is the same as the conjugate acid. And then you have the OH, the hydroxide, coming from your water molecule. So your products are your protonated base, the hydroxide, and then you have your base, the molecule of your base here on the reactant. So that goes on the bottom part of your equilibrium constant expression. No water because that's a pure liquid, and you don't have to include that one there. Now the actual value of your equilibrium constants, Ka or Kb, is giving you a lot of information. The smaller the value of your equilibrium constant for a weak acid or a weak base, the weaker the acid or the weaker the base. On your equilibrium constant expression, you have the ions, which is what you have on the product side, on the top part. And then you have the molecule of the acid or the base here on the bottom part of your equilibrium constant expression. If your acid dissociates a lot, you're going to have a lot of ions, and the number that you have in the top part is going to be big. Remember, if you have a lot of these ions here, you're going to have a small amount of what you have on the reactant side, because you're getting your products from your reactant. So the more of this one that it's converted to the ions, the less you have of this, the more you have of that, and the bigger the Ka. So if you have a small Ka or a small Kb, it means that your actual acid or your actual base, it's having like a super small dissociation. So you're going to have a small concentration of the ions on top and a large concentration of your molecule here on the bottom part of your equation, and that will give you a small number. So the smaller the value of your Ka or Kb, the weaker the acid or the weaker the base. And you have like some examples of weak bases. You have ammonia as a weak base, and you have some other examples which are actually derivatives of that NH3. Methylamine, ethylamine, and there are several others. So the value of Ka and Kb, as I already told you, you can use to predict like the strength of a weak acid or a weak base. So you can compare like several values of your equilibrium constants to say like which acid or which base is stronger or weaker based on the numerical value. But we actually use those values to calculate concentrations in solution. The type of calculations that we're going to be doing now applies to weak acids and weak bases. They are different from the type of calculations that we do when you have strong acids or strong bases, because for strong acids and strong bases, you don't have an equilibrium. So I have here a problem, and I'm going to use this problem to review like a couple of things. So we're looking at acetic acid. What you want to find out is the concentration of your hydronium ion in solution. For your acid here, you have a value of Ka. So the value of Ka belongs to your acetic acid here. So whenever you have a value of Ka, that it's telling you that it's a weak acid. You don't have a value of K for strong acids because there's no equilibrium for those. So if you don't have an equilibrium, you don't have an equilibrium constant. So to find out your concentration of hydronium, in your list of equations, you have this equation here, hydronium equals 10 to the minus pH. If you have a numerical value for the pH, you can use that to find out concentration of hydronium. But in this problem here, you don't have a numerical value for pH. You have a concentration for your acetic acid. Concentration for an acid is useful to calculate concentration of hydronium if you have your pH value. But in this case, you have a concentration, you don't have a pH value. If you have a strong acid, if you have a strong acid, you can use the concentration of the acid to predict the concentration of hydronium, and with that you can calculate pH. But when your acid is weak, even though you have 2 molar here as the concentration of your acetic acid, this is a weak acid, and not all of your acid is dissociated in solution, which means that you're not going to get all as hydronium in solution. When you have your acetic acid, this is your dissociation equation. The acid is donating the proton, and the water molecule is taking that proton to give you your hydronium. So even though your acid is giving you hydronium, we don't know how much hydronium you have in solution because this is an equilibrium. So whenever you have an equilibrium, we use the ice table to solve for whatever we need to find. In this case, we want to find out that hydronium concentration. So we do have an initial concentration of your acetic acid, which is 2.0. Initial concentrations for your ions, it's going to be 0 because you're getting the ions from the dissociation of your acid. Now we can predict by how much the concentration of the acid is going to decrease to give you the ions in solution. So you have 1 mole of acetic acid. That concentration, 2.0, is going to be decreasing by X amount. We don't know how much is X, but we can find out that number. Your initial concentrations here is 0. They're going to be increasing. You have 1 mole of hydronium, so this will be increasing by X amount. So your initial concentration is decreasing by X, and your concentrations here for your products are going to be increasing by an X amount that we don't know how much it is. So in equilibrium, we have 2.0 minus X for your acid, 0 plus X, which is just X, and 0 plus X, which is just X. So for my dissociation equation here for acetic acid, I have here my equilibrium constant expression is your hydronium times your acetate ion over the concentration of the acid, which should be C2H3O2 down here. So that's my equilibrium constant expression for this, not including the water. What you're trying to find out is the concentration of H3O plus, and that concentration is concentration at equilibrium because this is your equilibrium equation. Your concentration of hydronium in your equilibrium is given by X, which means that if we find the value of X here, we can determine how much is the concentration of hydronium because they are the same thing. So we can plug in your equation here, Ka equals H3O plus, and H3O plus in equilibrium is X. Your acetate ion right here, concentration of this one in equilibrium, it's X. Concentration of HA, which is your acetic acid here, in equilibrium is 2.0 minus X. The value of Ka is given in your problem, 1.8 times 10 to the minus 5. And that will be equal to X squared over, and now I'm going to do something. Look, your equilibrium constant expression is a number that is 10 to the minus 5. A small number like this is telling you that your molecule here for the acid has a small dissociation. This is your dissociation constant for acetic acid. So if you have a small dissociation, what you have is a small amount of your ions. Whenever the value of your equilibrium constant is 10 to the minus 4, minus 5, minus 6, minus 7, or in other words, anything smaller than 10 to the minus 4 equal to 10 to the minus 4 or smaller than that, we are going to assume that your initial concentration for the acid is going to be equal to the concentration in equilibrium. And that it's true because you have a small dissociation. So of your initial amount here, 2 molar for your acetic acid, just a minimum amount it's actually being converted to the ions. And you can predict that based on your number here. The smaller the amount of ions that you have here, the smaller the Ka, the more of your acid you still have in solution when you have equilibrium. So I'm going to simplify the math by saying that at equilibrium, my concentration is going to be equal to my initial concentration. That this concentration here is changing by just a super small amount. That is not going to affect my final number. My initial concentration, this means that it's almost the same as the concentration at equilibrium, and what I'm going to do here is just to write down 2.0. And now you can solve for x, which is what you're trying to calculate right there. 1.8 10 to the minus 5 times 2, and now you want x, so you have to do the square root on both sides to get only x. And I have x value of 6.0 times 10 to the minus 3. And you're trying to calculate concentration of hydronium. Concentration of hydronium is x, so that's the concentration that you're trying to calculate. Another possible way of you getting the exact same problem is, instead of asking you to find concentration of hydronium, I can ask you to calculate the pH of the solution. To find out the pH of the solution, you need the concentration of hydronium, because pH equals minus log of that concentration. So it's a similar problem. It's just asking you to find like a further step, because you still have to find out hydronium to get the pH. So since you already have here the hydronium concentration, you can actually calculate the pH value for your solution. To find out the pH, you just need your hydronium concentration. Minus log of 6 times 10. And I have two significant figures, 2.2. When you do minus log of your hydronium concentration, you will get something close to 2.2. You can actually verify if your numbers are correct. If you have an acid, your like what you have here, acetic acid, your pH should be a number below 7. Okay? So you can calculate and check more or less if your answer is correct. So there's another problem for you to solve. You have the answers there. So it's a very similar problem. You just have a different acid with a different Ka. But how you solve this problem, it's in the same way that the previous one. You have to be able to write down your dissociation equation. The products of your dissociation equation for a weak acid will always be your hydronium plus the negative ion in your acid, which is going to give you the conjugate base on your product side. You have to be able to write down your equilibrium constant expression. If you have your equilibrium constant expression, you can check what information you're missing to calculate whatever the problem is asking you to find out. In this problem, you're still calculating concentration of hydronium, and you can use that one to find out the pH of the solution. Now, this is a problem like the one that I was telling you, like a different type of question, but the problem is exactly the same. In this problem, you need to calculate the pH of your solution. Still a weak acid, so you have an equilibrium. And you know it's a weak acid, not just because you should know that acetic acid is a weak acid, but because you're given a value of Ka. Whenever you have a value of Ka, that's going to be a weak acid. So to calculate the pH, you need concentration of hydronium. In the previous problem, I calculated concentration of hydronium, and then with that one, we got the pH. In this one, like, you have to calculate pH, but you cannot calculate pH without hydronium. So I'm going to start by writing some things that you need and giving you like the final answer, and you can work the problem in a similar way than the previous two. You already have your dissociation equation for acetic acid. Let's review how to do that. Acetic acid dissociating in water. If this is the acid, it will be donating H plus because it's the acid. If it's donating H plus, your water molecule is accepting H plus. So whenever your acid is donating your proton, you're going to get the conjugate base, which is the negative part of your acid. Whenever the water molecule is accepting the proton, you're going to get hydronium. No charge, you have positive, negative 1. If it's losing your positive charge because you're transferring the proton to the water, you will get a negative charge here. The water, no charge at all, but now it's gaining a positive 1 from your proton, so that becomes H3O+. The acid, the base, and what you're getting here is the conjugate acid. And the conjugate acid is your base with the proton. And this one here will be your conjugate base, which is the acid minus the proton. There, that's to review your conjugates. So now you have your dissociation equation, and you can write down your Ka, which is going to be H3O+, your acetate ion, minus 1 over your acetic acid molecule. You still have to do your ice table. Initial concentration for your acetic acid is given. initial concentrations for your ions are 0, decreasing by x, increasing by x. So in equilibrium, you're going to have 0.150 minus x, 0 plus x, and 0 plus x. Now what you're trying to calculate here is the pH. Now you get to see why you need the ice table. For you to calculate pH, you need concentration of hydronium. So this is a weak acid, and for you to find concentration of hydronium, you need to find out concentration of hydronium at equilibrium. So to get that hydronium that you need to determine how much is X. So you're given the value of Ka, and this is the same problem as the previous two. You're given the value of Ka. Now you can plug in here your X's. In here, same thing that we assume when your Ka value was like 10 to the minus 5 actually, because it's the same problem. You can assume that at equilibrium, the concentration of your acid is going to be the same as your initial concentration. So assuming that you're going to simplify the math and you're going to find out the value of X, and then with the value of X you can actually calculate the pH of your solution. So I have a pH value for you. You should solve your problem and check your answer. Since you have, for the first problem and for this one, for both of them, you have acetic acid, and I calculated pH also in the first problem. You can think about the difference between your two pH values. It's the same acid, which means that you have the same equilibrium constant, but there's something that is different between your two problems. So you should think about why you have a different pH between these two problems. Now I want to do another problem because this one here, it's a little bit different. You have 3 examples with weak acid, so we need to do one with a weak base. So you're trying to calculate pH. Okay. And to calculate pH, you need ideally, that's what you need, right? Hydronium. We're going to calculate pH in an indirect way. So, in the previous problems, you had like a weak acid, and with your weak acid, you're getting hydronium as a product. Your acid is dissociating in solution to give you hydronium. But when you have a weak base, such as this methylamine here, I'm going to write down your equilibrium equation. Or weak base in water weak base means that this substance here, if it's a base, it's going to be accepting a proton. So the proton is coming from your water molecule. So I'm going to write down your water molecule as I did before. HOH. You have the positive part, which is your proton, and then you have your negative part, which is your hydroxide. So weak base, it's a base, it's going to accept a proton. The one that is accepting the proton is the nitrogen, not the carbon. Carbon here already has 4 bonds. You cannot add an additional bond to carbon, right? Carbon has 4 valence electrons. It can form a maximum of 4 bonds. Okay? So your nitrogen here is the one that is going to be accepting the proton. So nitrogen will go, instead of NH2, you will get NH3 because it's accepting a proton. So that will be CH3, NH3. You have no charge here initially, and you're getting a positive 1 charge. Your initial charge is 0, and you're gaining a +1, so 0 plus positive 1 will give you a total of a positive 1 charge. That's why that's a positive 1. This is an equilibrium. And then what you have left here is the negative part of your water molecule, because that proton is being transferred there. So the only thing that you have left here is your hydroxide. You see now, that's your equilibrium equation. Now, in the previous problems, you had hydronium as a product. So when you're solving your ice table, the value of X was the concentration of hydronium, and you were using that number to calculate pH. But here, the value of X is going to give you hydroxide, not hydronium. So I'm going to set up your Kb here, which is going to be your protonated base, your hydroxide over your methylamine right there. So your ice table, setting up your ice table, your initial concentration here is 0.33. For your ions, it's 0. They change. That concentration will be decreasing by a certain amount, and with that amount that you're losing from your base, you're going to be getting the ions in solution. So in equilibrium, that will be 0.33 minus X, X, and X. So if you check your problem, we can use our expression here to find out how much is X. And the value of X is going to give you hydroxide, not hydronium. We can assume this here. Okay? At equilibrium, your concentration is very likely to be exactly your initial concentration, because your initial concentration is decreasing by such a small amount due to that number there, that you can say that it remains almost the same. So in my Kb, I have here X, X, X for this one, X for that one, these two, over 0.33 for this one here. The value of Kb is 4.4 times 10 to the minus 4. That will be equal to X squared over 0.33. So now we can solve for X. So 4.4 times 10 to the minus 4 times 0.33. That's like 1.45 times 10 to the minus 4. And that's x squared. So you need to get the square root of your number. I'm trying to isolate x. So let's do 1.5, not 1.45. 1.5 times 10 to the minus 4. So to get just x, you need to do the square root of your number. You're getting rid of the square on this side here, and you get the square root, and then that will give you the answer for how much is x. 1.5. When you're getting the square root or any like cubic root or anything, if you have a number scientific notation, put in parentheses. If you forget about that, your calculator is going to get the square root of your 1.5, for example, in this one, and then the square root of your 1.5, it will do times 10 to the minus 4. Okay? So make sure that you put the number in parentheses. So this is like 1.2 times 10 to the minus 2. Okay? So that's the value of x. And the value of x is giving you concentration of hydroxide. If you have concentration of hydroxide, you can calculate pOH, not pH. For you to calculate pH, you need concentration of hydronium. You don't have hydronium from this equilibrium because this is a weak base, so you're getting hydroxide as the product. You can use your hydroxide concentration to find pOH. That's your pOH, and you're trying to calculate pH, so now you have to do an additional step to get pH. You have an equation that says that pOH plus pH equals 14. So your pH is 14 minus pOH. If you forget about this step here, when you're calculating, let's say that you're using the value of x to get pH, which is wrong, but let's say that you're doing that. If you calculate pH with that concentration there, you're going to get 1.9. 1.9, it's an acidic pH. What you have is the dissociation of a weak base, so you cannot get an acidic pH. That should tell you that you are missing something in your calculation. The number that you can get with that concentration corresponds to a pOH because this is hydroxide. If your pOH is 1.9, when you calculate your pH, you will get 12.1, and 12.1 is a pH value above 7, and that's a pH value that corresponds to a base. So I have here another problem where you're using concentrations to find your Ka value. So you're not given the value of your constant, but you're given information that is going to be useful to go all the way to your final answer. So you have your pH value, and you have an initial concentration for your solution. With your pH value, you can actually find concentration of hydronium. See? You can find concentration of hydronium if you're given a pH value. So that's a lot of information here. So I'm going to put here like a generic equation because we don't have a specific acid. This is just a solution. And remember that you're trying to find out your Ka value. So I'm writing down my equilibrium constant so you can see what you need in order for you to be able to get that value for Ka. So I have my Ka. If you want to calculate Ka, you need concentrations at equilibrium. Remember, whenever you're using a K equilibrium constant, all of your concentration, they have to be at equilibrium. That's why we actually use an ice table. So for you to get that Ka, you need concentration at equilibrium for hydronium, for your conjugate base, and for your acid here. Your initial concentration for the acid is the easy part, minus x, sorry. And that will be 0.175 minus x. Your ice tables, they always look the same. So I have my ice table there. So if you check hydronium here, it's x. And you can actually get the value of x from your pH. If you have 10 to the minus 3.25, which is the pH value, you will get the value of x, which is what you need to find out your Ka. There's something very important about this one here. Let me find out this one so I can tell you. I have 5.3 significant figures, 5.62 times 10 to the minus 4. Remember, this is hydronium. That's your concentration for hydronium that you're getting from your pH. Now that concentration of hydronium, it's your X value right here. So look, for you to get your Ka, hydronium is X, your conjugate base is X, equilibrium concentration and this is what I wanted to tell you. In all the problems that we did before this one, we were assuming that your initial concentration for the acid or the base was equal to the concentration of the acid or the base at equilibrium. And we were eliminating that X to simplify the math in your problem. In this problem, we're not doing that. And we're not doing that. We cannot do that because you don't have a value of Ka. We are eliminating that, assuming that your initial concentration and concentration at equilibrium are the same because your Ka it's a small number or your Kb it's a small number. In this problem, you don't have a value of Ka. So you cannot assume that your initial concentration and the concentration at equilibrium are going to be the same, because you don't know if you're getting a Ka that is 10 to the minus 3 or minus 2. Chances are that you still get a Ka value that is 10 to the minus 4 or smaller than that, but we don't know that. So if you're calculating the value of your equilibrium constant, you have to keep that one there. But that's not a problem, because you already know how much is X. So you just need to plug in that number here, here, and here, and that will give you your Ka value. And you should be getting a number that is close to this one. Okay?